Hey everyone, and welcome back to this class, the NumPy stack in Python. In this lecture we are going to start looking at the Scipy library. Again, just to reiterate, the goal of this course is not to show you every last thing in each of these libraries, but rather a select few things that are used often in my deep learning and machine learning courses. The idea is, if it's used often, then it's something you should remember. If it's not used often, then you're going to forget it anyway, and if you do try to commit it to memory, you're wasting your time. There is an opportunity cost of not learning more important things. Remember that if and when you need a specific function, you can always look it up in the documentation. This course will get you comfortable and familiar with these libraries, so that when you do eventually need to go look something up in the documentation in the future, it won't be too scary. The most common distribution is the Gaussian. We've already looked at how we can sample from a Gaussian distribution. One question that is common to ask is, given a sample of a random variable, what is its probability density? You should recognize the probability density function, or PDF, of the Gaussian as this equation. Now, we already have all the tools we need to calculate the value of this function. We know how to take the square, we know how to divide, we know how to exponentiate, and we know how to take square roots. So why are we even discussing this, you might ask? Well, of course, Scipy gives us a better way to calculate the PDF. In fact, you should always use Scipy if possible, because it will be much faster. First, let's import the norm module. So one thing we can do, for example, is find the probability density of 0 from the standard normal distribution. So that's norm.pdf of 0. Of course, you might be working with a Gaussian that has a mean other than 0 and a variance other than 1. So you can pass in those arguments into the PDF function as well. So norm.pdf, x equals 0, mean equals 5, and standard deviation equals 10. So note that the scale parameter refers to the standard deviation and not the variance. So this is a standard deviation of 10, which corresponds to a variance of 100. And as expected, this has a much smaller probability density. Often, we need to calculate the probability densities of many different values contained within an array simultaneously. Your first instinct might be to use a for loop to calculate each of the PDF values individually. But of course, this is not the best way. Like the NumPy functions, this function also gives us a way to do element-wise calculations. So if we have a random array, we can calculate the PDF of all the values at the same time. A common calculation we need is not exactly the PDF, but the log of the PDF. When you want to calculate the joint probability of some samples of data, you need to multiply them together. But if you calculate the joint log probability, then you can add all the individual log probabilities together. As you know, adding is a cheaper operation than multiplying, so this saves us time. Because the form of the Gaussian is exponential, when you take the log of an exponential, the exponential goes away. So this also saves us time, because the exponential is also a costly operation. So a lot of the time, it is advantageous to work with the log probability rather than the actual PDF. Conveniently, there's a function for that too. So that's just norm log PDF, and you pass in the values. The last thing to talk about here is the CDF, or cumulative distribution function. Recall that this is the integral of the PDF from -infinity to x. Also recall that this integral is not actually solvable, so you can't find a mathematical expression for it. What you can do is compute it numerically, and of course Scipy gives us a function for that as well. So that's just norm.cdf of r. And of course there's also the log CDF.